because thanks to them, quantum computing has become very popular in India. They have taken a lot of initiative. Many times we have talked of late online. For example, they helped in QIQT, where I was giving a talk. And they have been really, really open. Many, many research papers have come out thanks to the initiative of IBM. And, they will talk more about that. But first, let me introduce Sukumar Pradhan. We are classmates. And he is the founder of Flick Microwave. You please check out, the site. You'll find out a lot of advanced technological applications have come out from his laboratory. I would say it's from his laboratory and his company, finding huge application in defense. I would not see, for example, I was in Hyderabad for 10 years in Hyderabad Central University. He has been sponsoring many of our conferences. Me, Professor Suhas Chaturvedi, one of the well-known quantum computation person in India, Professor Srinivasan, we used to regularly go and wonder how he is able to design this kind of technological applications, which was like a jammer, electromagnetic waves, use of electromagnetic waves, particularly microwave. And, I remember very distinctly when Professor Chaturvedi asked him, he said, I literally see propagation of electromagnetic wave or the so-called microwave inside this thing. So I can really control, I close my eyes. He is that good. All these problems of Jackson, which many of us find very difficult to solve. He has solved all of them. So, quantum particles are waves and particles. So he's dealing with waves. But, once the wavelength becomes small, number becomes small, we know microwave domain, quantum effects are coming in. So you can check Raman Research Institute, Professor Upasisina, has already done quantum experiments using microwave. So one of my motivation is to motivate Sukumar, push him towards quantum technology. And who are the better people than our IBM colleagues in India? So with all this small introduction, I request Sukumar to take over and chair this session.
Thank you very much, Dr. Panigrai. Yeah, he was my classmate, but he is in a platform what I admire him, and in his field he has excelled. Thank you very much, all the panel members, IBM's, the team which is here to present in this session for the special session for quantum information and quantum technologies. When the invitation was given to me, I was really very much excited and inspired to share this, though it is a learning point for me, because as he has already told, I was in the Schrodinger equation front, but now it is the quantum front. When the wavelength becomes very, very small, so the quantum mechanics come into picture, comes into our rescue, comes into our application front, and that is what we are seeing now. I mean, with the amazing beauty of quantum mechanics in the industry by the invention of the quantum computers. Till now, actually, we were seeing our mechanical, mathematical application, we always see with binary, that is on and off or 0 or 1. Okay, all of you know. But we never had imagined that there will be different states what our machine also can understand. We can understand different languages, right? There are so many languages in this universe. I mean, in this world, what actually we have already come across, we have understood. But now, the machine to understand a language and then to know that they know that language is the real invention. I really thank the IBM team who has inspired all of us in this particular area. So the qubit concept has really revolutionized the total, our knowledge front. What actually in our wisdom we always see a machine is able to do much more than what we can by the use of this qubit principle. I was just asking in the morning, my friend, by using the qubit, how many different states you can? He told infinite. Yes, of course, the phase variation, you can quantize the phase in infinite ways. But The usable is IBM has claimed up to 50, and Google has claimed up to 56. That's what the information I got. But basing on this, this is really a good beginning. I don't know. This may be considered as a historical event in India, so that people will be from this country, and okay, this is a world is the real forum. We can go to the much deeper into that, and we can find an application where industry also will bring it forward for the use of our society and community globally. With all these things, I welcome you for this session. And this session, we have named it as Recent Developments and Application of Quantum Information and Quantum Technologies, QIQT. This session is specially formed as a first of its kind in India in this particular year for the industry and academia interaction in the QIQT field. As all of you know that I have already given an introduction about the use of quantum mechanics in the industrial platform, in the computation overall, now actually in medical field and in different aspects of our life, we apply it and make the best use of it. With all these things, I thank you for giving me this opportunity. And I also I welcome all the participants, panels, participants, everybody to take full advantage of this system. There will be 3 papers, which will be 3 presentations, which will be given. And the first, all from the IBM group, I think. And the first one, actually, I welcome Mr. Sayantan Pramanik. And
I think it is Dr. Raghunathan.
Dr. Raghunathan. I think I'm sorry, this mail which has received me. Could you please tell Mr. Dr. Prashant? Could you please tell us about Dr. Raghunathan more?
Dr. Raghunathan has been with IBM India, leading IBM India, and IBM has been very active in India in conducting schools and introducing us to IBM platform. They have their own language. So they have been really conducting, and they have a lot of, talks which are available to teach the students to use of IBM. IBM, in fact, have a lot of, quantum computers available. They make, starting from noisy 5 qubit to start with, to do various kind of things. Many of them, they allow the students and faculty members to use. So now, for example, Government of India is also using their platform. So they will, Dr. Raghunathan will speak more specifically about that, but they have been pioneers in quantum computation all over the world.
Okay. I welcome Dr. Raghunathan of IBM to now come forward and give us his paper and tell us about his work and his vision, how actually he sees the industry and the participation of industry and academia in this field. Thank you very much. I invite Dr. Raghunathan to come and give the first lecture.
Thank you. Hopefully you can all hear me.
Yeah, it is audible.
Yeah, I thank.
We can hear you. No problem.
Yeah. I thank Kaiser for the opportunity here. I'm glad that an event of this magnitude is happening. Hopefully in the near future, we'll do it in person, but nonetheless, glad. In this talk, since this is a keynote talk, I want to give a broader perspective, and I want to comment on some of the things that IBM has been doing. What I would like to cover here is give a sense of what is happening all around in terms of the technology, in terms of the adoption. I will also briefly comment on the research directions so that audience here get a sense of what are the kind of problems that people are exploring. And then also how you can get started and engaged. I think the number of charts I have are probably going to take about 40-45 minutes or so, maybe less, we'll see. And then we can have a broad discussion. Since you're going to have a lot of students in this platform, I'm guessing that there will be a lot of questions. So I'll try to keep it as broad and brief as possible so that we can have discussions at the end. Okay, so now quantum computing in the near term. I specifically mentioned near term because a lot of comments that I'm going to make will be about the processor architecture that IBM is coming out with. And then what does it mean, how people are adopting, how things are changing in the recent past, and how we look into the future, and what are the challenges that we are facing, we're going to face, and what are the interesting research directions to go after. So given all this, I'm setting the context of quantum computing in the near term as what I want to talk about. So we are at a very interesting point in the history of computing, where probably for the first time we are branching in terms of the model of compute. As was mentioned a little earlier, thus far there has been bits, which has been the fundamental unit of information, and it's coming out of basic classical physics. And that bit is binary, deterministic. Unlike quantum, where the fundamental unit of information is called a quantum bit or a qubit, though it has two states, 0 and 1, but it's a quantum state, which means that you can have different combinations thereof. So we are now moving away from a basic bit of information coming out of pure classical physics to basic unit of information coming from quantum physics. And that also means that the model of compute now is different. It's moving from fundamentally deterministic to fundamentally probabilistic. So this sort of is a unique point in history insofar as computing goes, where we are now seeing both. I do want to like to comment that it doesn't mean that one supersedes the other. It doesn't mean the future that we are seeing is completely quantum and there is no room for classical. In fact, the more and more we understand for foreseeable future, what we are seeing is a hybrid model where quantum and classical will necessarily have to coexist and take it into the future. There are certain tasks that classical can do very well, very efficiently. We should leverage classical for that. There are certain tasks that quantum can do efficiently and use quantum for those. This cartoon gives a broad view of the kind of problems that you would want to do in classical, perhaps, and the kind of problems you want to do in quantum. The white oval are the problems that classical can do very efficiently. Think of multiplication, division, and other normal things that we do with our computers every day. The light blue problems are the ones that are very hard. The hardness could be because it has a lot of computation to do, or the amount of memory required is very large in both cases or combination thereof. So it becomes a hard problem, so you cannot solve efficiently with classical. What quantum is providing is a potential and a hope in that you want to be able to, it opens up a space, this dark blue area, where you can address certain problems that classical computing cannot. For example, the factoring. So there are certain problems that quantum can solve efficiently that classical cannot. And in the future, what we're going to see is a sort of a hybrid model where classical and quantum can coexist. And also in the future, as quantum matures, the kind of supercomputing that you're going to see a quantum centered supercomputing where you will have different kinds of compute elements in the server form, as it were. You'll have classical CPUs, you will have GPUs, you're going to have quantum processing units as well. So you're going to have an amalgamation of all that. And based on the particular problem at hand, based on the particular kind of solution that is needed, you're going to map it to classical, and you're going to map it to GPU, perhaps you're going to map it to quantum, and then that's how the computation is going to emerge. Before we go into the details of some aspects of this, let's talk about the adoption, because this is a very unique and interesting point in history to just look at how people are approaching this technology is just as interesting. So here is what we are seeing is an exponential growth in the adoption. This is a map of basically the colors is telling a ping from that particular location to one of our quantum servers. What that means is somebody is running some experiment from some of these places into our quantum. They are running experiments. So on the bottom, what you are seeing is x-axis is time. I think it starts from 2016 when we first put this machine on cloud. to the present day, probably a year back, June 2021. So you can sort of see the trajectory. So initially it was slowly, and then as you can see, it's growing exponentially. The red curve is the simulator, and the blue is the actual run on the quantum hardware. What is heartening to see is that we are sort of seeing major centers where there is more and more interest in adoption. You can certainly see the Western Europe, then the eastern coast of US, and then you also see that India is doing a lot of work here. A lot of people are playing with the system. And certainly there is Japan, where there is a lot of work activity, and the southeast coast of Australia. So you can sort of see clusters developing where there is a lot of interest, a lot of people are playing with these systems, trying to understand what this is all about. And perhaps a lot of students are also doing some research along the way using this hardware. And so the adoption in time has been exponential and growing pretty rapidly. I'll comment on why that is so in a bit. But what I'm glad to see is also that India is becoming more and more of a cluster here with wider and wider adoption. I do want to see more and more contribution in the research front in terms of coming up with key breakthroughs in the
बारिश कब
algorithms.
रहेगी?
Sorry, was there a question? Okay, so hopefully in the times to come, with more and more adoption and more collaboration, perhaps we'll come up with some key breakthroughs in this technology that will move the technology even faster and sooner. So as I said, IBM first put the machine on cloud in 2016. So initially the idea was more from education standpoint. It was more about having students play with it, learn quantum physics and quantum computing perhaps, and then see how this works, and maybe try out few experiments and such. But then it took a life of its own. Now we have come 2019, we had a full-fledged integrated machine. This is system one, where you had overall framework that could essentially sit on a data center. This is the chandelier. If you open this thing, you'll see that kind of chandelier. This is the fridge portion at the bottom of which sits the processor. And this could sit in the any data center. We moved from a simple sort of processor that would sit in any physics lab, perhaps with a lot of wires here and there, to a full-fledged integrated machine in the span of 2 to 3 years. What is amazing is some of these stats. We now have 20 plus machines now on the cloud. We have 180 plus members in the what we call as a quantum network. What is unique is the 410 plus K plus users, unique users, have been using this system. And 3.5 billion executions have been run. So you're on average running 3.5 billion circuits on physical hardware across all the hardwares that we have. This is the kind of numbers that we are seeing, which is quite humongous. So I'll comment on these metrics. These are very important. I have some charts there. So we track 3 metrics: the size of the machine, the quality of the machine, and then how good is it deployed in cloud. So here is one sample example of a machine called Washington, which is 127 qubits. But if you want to go look at all the machines, you will see them in this particular link. If you go to services there, we have about 24 machines online and growing. What is interesting is that over 1,400 papers have been written on top of these machines. And as I mentioned earlier, we are averaging 3.5 billion circuits a day right now, and it's increasing. And overall, in the last 5 odd years, for 6 odd years since it's been on cloud, we have seen trillion plus executions that have been run on the actual hardware. What is also important is while the initial idea was education, it has become a tool for research. And for example, in the APS March meeting, if you see the number of papers that use IBM quantum systems in their research work, you can see that there is a steady increase. Now it's become substantially higher compared to what it was earlier, but it's been consistently increasing. So it's become a platform for research from across different domains, be it physics, various aspects of physics, to quantum chemistry, to applications like drugs, battery, and whatnot. It's become a platform where people try to try to play with, and that's become a tool for research. In terms of industry, you can see that there is an array of exploration from various partners. You could imagine the kind of partners range from academia who have academic interests to CERN, to healthcare Amgen type thing, to Daimler looking at battery, to BP looking at various explorations and energy related things, Boeing looking at corrosion or any other event. So there is a wide array of exploration from different kinds of industry into this particular space. So let's now get down to the metrics. So you saw that the three metrics that I had shown a little earlier: scale, quality, and speed. These are the three major metrics that we measure a performance by. Many times in the popular press, qubit sort of is the default connotation for performance, which is not exactly correct. It is one of the metric. So for example, the scale here would be that. Quality would be how good is the hardware. And speed is when I deploy it in cloud, how quickly can I make it work? And this is also equally important. So all these three metrics together defines for us the performance. And in each of these machines that you see deployed, you will see three numbers that we put out. So scale. So earlier this year, we put out 127 qubit machine on cloud called the Eagle processor. So what that is that now we've crossed the 100 qubit threshold with this particular processor, and that's a very important and interesting space to be in for many reasons. One is that till probably the previous highest processor that we had was about Hummingbird, which was 65 qubits. It was in the margin where classical could do in a supercomputing space, could do some calculations or simulations that could simulate some of the 60 odd qubits in certain cases. But now with this regime, we are entering a regime where classical will not be able to do simulations of this level. However, the other aspect of how good, while we have the capacity in 100 plus qubits in the quantum space, the state space is quite large. We do need more and more better quality systems so that we have more control over all the state space that we possibly have. But what is interesting though is we are now entering the regime of unknown. We are getting into a space where this is beyond classical. And what is interesting is to start exploring this space and see where we can potentially get a quantum advantage. We're gonna have 433 qubits by the end of the year, and next year we're gonna have 1,000 plus qubits. This truly takes us into a regime that is purely the problem spaces that potentially quantum can only solve, and the engineering and the technology that needs to go in to solve and to get quantum advantage will be the aspect of research that we'll be looking at. I commented on the quality. This is just as important. So remember, so quantum volume, QV stands for quantum volume, is the metric that we track for quality of a qubit. So it is a combination of various elements that goes into this number. So this is constantly increasing. So for example, recently there is a coherence breakthrough. So what that means is the T1 time is increasing quite a bit. And it's been increasing consistently so. So if you can see, so initially the Falcon R5 class of processors, you had the T1 time which was hovering around 0.1 or so milliseconds. And then R5 generation was hovering around 0.3. Now in the test devices in the Falcon R8 regime, you're looking at 0.6 and quickly moving towards 1 millisecond T1 time. What this means is that we are having the coherence time is larger, which means that the circuit we have a lot more time to do our compute, and it's alive for that much longer. The other aspect is the gate fidelity, the quality of the operations that we do. That is also crossing important barriers like 99.9% with some of the more recent test devices. That's important because while both aspect of having the circuit live for longer and also being able to do computation efficiently, both are equally important for us to get the right results. And then there has been consistent improvement in the software stack to use this hardware more efficiently, and that's the transpilers that are happening. And externally, the controls are getting better so that the noise that is imparted onto the hardware due to controls and other mechanics is also reducing. So it is an integrated system level development that is happening that is leading us to move the ball further and further, improving, and we're going to be reaching 1024 quantum volume soon. And that leads me to the quantum volume part. Why is so much interest and excitement? And that is because of this particular plot. So on the x-axis is time, on the y-axis is the log scale of quantum volume. As I mentioned, quantum volume, think of it as a stand-in for quality of the hardware. The higher it is, the better it is. You want it to be as high as possible. So what you're seeing is that this has been increasing consistently year on year. IBM in 2018 had said that we're going to double the quantum volume every year. Now we are sort of beating that and doing it faster and faster. If you see the time frame, we have 2 points in 2021, 2 points in 2022. This is not just 1 year. So we are doing every 6 months now. And you can see that this is going faster. Now we have gotten to 256 and probably we're going to get to 1024 in 2022 by the end of the year. So it's growing very fast. So what this is telling us is that the T1 time is increasing, the quality is increasing. And once we have more and more quality, and then the quality vector is increasing exponentially rapidly, this is giving a sense of the Moore's law on the classical side, right? So this growth of the quality and the control and that we have on the hardware and the improvement of it is what really is having the feeling that, yes, this is moving in the right direction, moving in the right direction at the right pace for us to pay more attention. The next part is the speed of the applications, the last metric. This is just as important. See, for practical deployment, for anything to have quantum advantage, you are going to compare the performance against the best supercomputer that you're going to have at hand, which means that everything matters. And also, if you don't keep track of the cloud deployment, there are different timescales within the cloud deployment. So if you look at it, you're going to have the quantum hardware here on the bottom right. You're going to have the execution kernel. This is classical hardware. You're going to go back and forth between them. Remember, there is an iteration, and many times if you are using variational algorithms, there is a back and forth happening. And that is in the near time execution time. And then at the outer Q layer is the Qiskit program running, where the classical program is calling these things. So you have near time and the real time, two different time scales. And you want to be able to run this iteration plus this variational type circuits faster and faster. All these are very important for us to realize something of true value in real time. Plus, also note in the hardware side, the readout or the measurement time is increasing quite a bit. It is now 15x faster to read out. Measurement was one of the important source of noise. One of the reasons for it being, along with it being complicated, it was also taking too long. Now it is drastically smaller in the latest generation, the R5 version. You can see that the average time has gone from 5,000 plus to 300, which is drastically different. With other error mitigation techniques and the performance that we also gain from this, it's that error and that kind of noise that we see in the system will be reduced. Plus the speed of this makes real practical difference when you especially are looping over millions and millions of runs, millions and millions of circuits in an algorithm. All these add up to something significant. So for example, with Qiskit runtime, so this is a lithium hydride simulation. IBM had done a paper on this. This was on the cover of Nature in 2017, I believe. They had run, at that point, they had run for 4.8 billion quantum circuits. And the time was, it used to take about 5 milliseconds per circuit. Now, the same thing has now reduced to 5 microseconds. Look at the difference in the total program runtime from nearly a year down to few hours. This kind of calculation tracking the runtime of deployment matters for us to be able to achieve quantum advantage. So for us to achieve quantum advantage, it has to be realistic and this kind of numbering, this kind of tracking, and therefore the metric speed is vital in making sure that whatever we develop is practical and implementable. Aside from that, there has been improvement across the stack. You can see that QIQT runtime, the near time cycle, the looping, inner looping. Earlier, it used to be the program sending the circuit, running it in hardware, getting the result, and it was all looping like this. Now, it is handled inside the cloud and managed from within the cloud. Then there is algorithmic improvement, software stack improvement, the control, and the device readiness. Overall, you're seeing improvement of 120x in the latest generation of the QPUs. So overall, the performance, as I mentioned, is scale, quality, and speed together. Value, however, for the end user is not just performance, but also the functionality, things that you can do. Recently, some of you may be aware of the services that we put together. That is additional functionalities that gives more and more abstraction beyond the programming of it, where you can program at the runtime, so use runtime services for most of your tasks, especially if you're working at algorithmic layer. And then the frictionless part is the programming should be pretty much identical to the way you program your classical hardware. There shouldn't be any major difference. And the platform, the tools, the packages that you use, and the way you use it should look and seem and work identical. And that's what frictionless is all about, the delivery part. And all this coming together is when we add value at scale. And that's when we will get to some sort of quantum advantage in times to come. Okay, this is an important chart. What is IBM's roadmap looking next 3 years? So at the bottom, let me explain this chart. It's a little dense. On the top, you see the years, 2019 to 2025, and then beyond. On the y-axis, you will see system modularity. So on the bottommost are the actual processors. These are the names of the processors. And then comes the kernel. So think of it as firmware, a layer above the hardware. And then you have the algorithms being developed on top of it. And then the model is the application layer. So that's how you would see it at different stack. I would want to focus on the lowest layer, which is the hardware. So we put out Eagle 127 qubits. It was on time. Latter part of last year, that's available. Osprey, which is 433 qubits, is on course for this year. Condor is going to be available next year. There are a couple of other variations coming through, which I'll talk about in a little bit of detail in forthcoming charts, but I'll give a flavor for it here. So for this, in the 433 qubits, you're going to have dynamic circuits. Dynamic circuits means that you could measure fast and you can do feed forward and classical feed forward and feed backward. That opens up new avenues of applications to explore. At this point in 2023, along with Condor being 1,000 plus qubits, you have Heron processors, which are connected by classical bits. And this is bidirectional. What this opens up is local operation and classical communication based computation. I'll comment on that as one of the research opportunities or some active area of research, why that is so. And also, otherwise as well, you can do multi-threading here, especially if you're doing expectations and you have to run the circuit a number of times, you can parallelize them very straightforwardly. But you could do a lot more than just simple parallelization. I'll comment on that. The next generation following that, if you see the cross build, there are two different things here. One is, I'll comment on this a little bit in the forthcoming chart, making it 408 using a different kind of communication. So I'll touch on that. Flamingo is you're using the Heron processor, but you're going to connect it slightly differently. I'll comment on that as well. And finally, the two ideas of this cross build and Flamingo coming together in the Kookaburra in 2025. So this is the set of processes that are in the pipeline for the next 2 to 3 years. So when we get into the 2024 regime, we're going to look at more error suppression and mitigation after we are done with the threaded thing. And then eventually we'll get to the error correction portion. This will be at the kernel level. But at the layer above, you're going to see an interesting movement. And now we are moving towards cloud deployment. So which means that you need to have serverless container-based deployment. You saw the QIQT primitive, that QIQT runtime primitive. So those things will be deployed in the serverless. So that's going to come make available next year. And once we have that, then international intelligent orchestration and circuit knitting. And this is a very important element. I'll comment on this briefly. That becomes very, very important in leveraging these processes more effectively. So these are the important elements of this roadmap. As you can see, we have delivered on all the goals that we have already done. And for this year, we are on target to deliver these two aspects. And hopefully we'll be on target for the process that we are looking at in 2023. Okay, research direction. So let me elaborate a little bit more on what is the kind of architectures that are coming about. So for the Heron processor that is coming up, what you see is the individual process. Each of them is a processor here, and they are connected by a classical bit, and this is bidirectional. So what this opens up is the kind of problems that you can do with classical communication and local operations and classical communication. Or at the very least, you should be able to parallelize your circuit averaging that we do, or the sampling. The next generation that you're going to see is abutting of the two processors by actual quantum communication. So this is one machine, one processor, and the other processor, and they are communicating through quantum channel. And so which means that in essence, they are behaving like one processor unit. And then what that means is that this is, in terms of the quality of this particular connection, may not be as good as some of the other ones internal. And that brings up an interesting challenge to the software stack to use this more efficiently, these barriers where these connections come about. How do we use it in an effective way so that the computation gets the value of the bigger processor whilst paying least cost due to noise that may come about, because these are likely to be more noisier than some of the other ones in the processor. The next generation is when we have classical communication. This is quantum communication. This is the abetted one that I'm telling you about. And then you have the classical communication happening across them. And then you will also be looking at quantum communication across them as well in times to come. So this becomes a multi-chip quantum processors. What this one is giving you is, this is giving you a sense of how the processor is going to scale. And the scalability problem is what is being looked at here. How are we going to scale up the processor and scale out the processor? And we would want to be able to do that by abetting them, connecting them through wires in classical communication, then going into quantum communication within the fridge, then across the fridge, and so forth. So that's how we're going to scale out the processor. What that means is that how best do we use the hardware then becomes an area of activism. Circuit knitting is when you use quantum and classical computation together. Now you can see that classical becomes embedded within the overall quantum context as well. So what is the broader idea of circuit knitting? Is think of this A and B. So think of the top portion colored light cyan, I guess, and then the light purple as two different processors, right? And the computation happening, the ones colored pink or dark pink are the computations that are happening for circuit across the two processors. So what you would want to do is essentially would want to be able to do use LSOC model to be able to implement the same thing, but using single qubit or local operation, and then use the classical communication to implement the same circuit. Now the challenge, of course, is that this will be an exponential problem, but then from practical realization, this is where the research opportunity lies. So I'll talk about 2-3 different ideas that are there as part of this. Embedding. This mostly comes from quantum chemistry space, where you have big molecules, perhaps. What the idea of embedding is, can we use can we look at the overall system and say the portions, there will always be in many chemistry things, you will have portions that are highly entangled, and then there are portions that are weakly entangled. The idea is find the active region as those that are highly entangled, strongly entangled, and do that in quantum processor. And do the other ones in the classical processor and do various stitching as needed to make it work. So that's the idea of embedding, and there are some references that you can go look up. Entanglement forging was a more recent paper. There you use Schmidt decomposition essentially, and you map the two problems into a reduced set, use classical communication. What you're trying to do is, in this particular paper, I think they took a water H2O molecule and tried to, with 10 orbitals, they reduced it to 5 and solved it using the processor, and with classical communication. You could classically forge an entanglement. The research challenge is that the cost of classical entanglement is exponential naturally, because you have to do all sorts of things. However, if you are smart and if you do intelligently, and if you know, identify portions that are weakly entangled, strongly entangled, and so forth, the weakly entangled ones, maybe with certain epsilon, you can cut off on the kind of calculations that you need to do. And practically, this may be identifying some set of few things that you need to simulate classically, albeit exponentially, but classically. But the numbers could be small. And also the circuit cutting is, how do I divide the problem? How do I divide the circuit in a way that for example, the connections between the two regions, ideally a bipartite, but if not, the connections are minimal, so that the cost of doing all these aspects, that is things that are between the two regions, is minimized, and you can control it through some epsilon, so that it becomes more and more practical. You will have n number of different applications that have this kind of signature. And in general, also quantum computation in general is likely to have features where there are certain qubits that are strongly entangled and certain others in the regions where they are strongly entangled and the connection between them is weakly entangled. This opens up a space in the research. And I think this is a very open area of research. Some initial work has happened in the last few years. I think now we are at a point where the hardware and the hardware architecture is coming to a point where this could be tried out in empirical fashion, and then you can propose some hypothesis, test it out in actual hardware, and then make the case for the algorithm. So there is a very open area here and possibility to do more research in this particular space to see, based on the architecture that is coming about and evolving, what would be the best strategy, how best to use this, how best to do the balancing, how best to use the quantum effectively, how best to reduce the problem into quantum, use classical where needed, or cut the problem into the spaces of highly entangled and lowly entangled and embed them and use it differently. So all these are different aspects of the same element. How do I use the hardware in an efficient way to solve a bigger problem potentially? And that's the idea of circuit rating. And I think this one will have a lot of interesting research results coming through in the coming years. And also, while the architecture comes and becomes open and a lot of folks can play with it, I'm sure there will be a lot more innovation in this particular space. What is also interesting is this is a theoretical work. What I'm more curious about is the plot here. In terms of simulating a quantum circuit, quantum simulation, the simulation cost, as many of you know, using a classical computer grows exponentially. And with error mitigation, this is the quantum cost as we have. And error correction is pretty much flat because it's more efficient. But we are very far from that regime in terms of error correction. We are in a regime where potentially we are in the border area somewhere here. In terms of, we have not realized a problem that has quantum advantage, so which means that we are inside this curve at this time, till such time we flip over onto the other side, but we don't know when that flipping over will happen, which means that we are in an interesting regime where for the first time we probably find a problem with quantum advantage and flip it into this space where it is beyond a classical, and you have a quantum solution coming through that can be run in some realistic time that adds value to it. And we're probably going to be in this regime for a little longer as we work our way towards quantum error correction. And so what it is that we are in a very interesting and unique point in history where we are at that potential point where we could demonstrate that quantum can add value beyond classical. And in this regime, there is a lot of research and opportunities available to go explore, both on the theoretical front as well as empirical front, in terms of the algorithms that can potentially take us there. So I suspected there would be a lot of folks with condensed matter. I'm not a condensed matter expert, so I'm just flashing this just as an FYI. This has now attracted a lot of interest in the condensed matter physics domain. Here are some references to folks doing work in this particular space and doing simulations in condensed matter. I'm hoping some of you in this forum will find this interesting. While this is condensed matter, and the other side is the particle physics, there is also research in using quantum computer in some of the simulations in the particle physics and also in high energy physics. And there is a lot of work that is now picking up in this particular space, because the quantum computer now is getting to space where it's becoming more and more interesting for folks to go try and solve certain problems there. So achieving quantum advantage will require us to be able to do a sequence of things at algorithmic level. So it's very unlikely that you're going to have one chunk, take it to quantum, solve it there, and be done. It's going to be a series of things. That's the potentially the way we're going to get to quantum advantage. So what I'm seeing is some representative chart here, where you have a classical, and then you have a sampler, and then the estimator. These are the typical thing that we do in our classical, and these are the actually the Qiskit runtime services that we currently have. So you sort of have a portion of the algorithm running classical, and you have something else running quantum, and then you have different flow, and then the overall thing is going to demonstrate that you're going to have advantage. So the eventually, when we do get to an advantage, the workload, the flow of the workload is likely to be in this form factor. Now on the application side, there are three broad categories, three general areas where this is going to be looked at. One is the simulation part. As many of you know, simulation is the origin story of quantum computing as we know it in the modern times, simulating nature as it were, or simulating physics or quantum physics. You can think of areas like quantum chemistry, material science, or high energy physics, and now condensed matter as well, as domains where you're exploring various aspects. And then you have data with some structure, and naturally that means that you have artificial intelligence or machine learning coming into play. So you have better model training, or sometimes fraud detection, or perhaps classification, better classification, lesser false positives. And then you have the classical optimization Monte Carlo type simulation, which gives us some additional value. Here are some industries looking at various applications in their own domain of interest. So Amgen is looking for health records. These are health insurance company, if I'm not mistaken. Then you have Boeing looking at problems related to perhaps this is logistics, routing perhaps. Then ExxonMobil looking at accuracy of energy surface calculations. So this is in their energy domain, and then Woodside is using data science for their workflow. So here is a little broader and the same set of categories, but a little bit more broader set of applications. So a few things that I'd like to highlight is the battery. There is some work that IBM and Daimler did, and looking at different kinds of batteries. So as you know, lithium hydride is the default model. Lithium ion batteries that we have is the default battery model. They are looking at lithium sulfur and other combinations for the battery. The implications of some of this, if as the quantum computing evolves and becomes more and more powerful, and if we do have a better battery technology, the implication is very broad and very deep across the society, as many of you know. The green energy, for it to have, we need to have better batteries for us to adopt electric cars more widely, or for us to use solar or any other natural energy sources. We need battery that can store more, that has higher capacity. So some of these problems that you're looking is very broad, very important. Drug discovery is just as important. Naturally, you're trying to do simulations at molecular level. And then you can look at on the finance side, there are problems like portfolio management, risk analysis that leverages some aspects of optimization or artificial intelligence. And then going to risk adoption pricing, risk analysis, vehicle routing. These are optimization problems, and the risk analysis uses the Monte Carlo that gives polynomial time benefit. So there is a broad array of problems that are being explored in these three general categories that I mentioned earlier. So BCG put out this information, their estimation. These are some numbers based on different industry. What is the kind of industry we are looking at tech maturity? So eventually I think tech maturity there is 2030 plus by the end of the decade. So you're looking at various areas where it's going to be multi-billion-dollar industry using quantum. Finally, I'll make a comment on education ecosystem. That's just as important as research and any other application development. So quantum ecosystem is developing very, very widely, particularly in the recent past. I talked about the research papers before, but look at the numbers in the education side. We are looking at, cumulatively, if you see, we are looking at 5, 6.5, 7, about 7.5 million in the last, 2 years of data that I'm showing here. So there is a lot of interest. There is a lot of education developer as well as community education that is happening. And IBM has been involved in a lot of these activities. So a lot of developer education is just as important. You need human resources to be able to be ready for the revolution that is coming. To leverage the technology and the value it brings, you need people in the pipeline to be able to do various activities along the product scales. To do from the developer to the researcher, you need everyone to be able to do this, and the education becomes important in that space for it to become reality. What this also means that workforce development is just as important. So IBM had the first perhaps developer certificate program that we had. Student education is important, as many of you know, and also as a professor mentioned earlier, we are very active in this space. The community development is just as important. Digital education, cascade-based problem, the lectures, the courses, the hackathons, we run many of these things. We are very active in this space because it's important for the workforce development, for it to become a reality, for the technology to become reality. In the Indian context, last year, we are working with many institutions to have them sign up with the Educators program. More and more institutes are joining. Basically, the idea is to provide access to these hardware for educational purposes. If you have courses that you're offering and you want labs and you want students to try out machines as part of the lab work, there is an educators program where you get priority access as part of your coursework. The students can go access them and do their lab work in our actual hardware and learn from it. So this was last year, and I think this will be increasing. We'll want to have more and more folks use this particular program for their coursework. The other is the future generation training. Specifically on the digital channels was one of the things that I highlighted a little earlier. We have about 3 million plus folks who have started using that and learning. Learning as an open source, you can see that in online textbook learners, you have 442K. So 500,000 people already there in there. You have Qiskit, Slack, Twitter, and other social media platforms. And then you have the hubs and other platforms where we do the training element as well. So all these put together provides a portfolio where we have invested a lot in terms of training and getting the next generation out, along with putting machines on cloud for the open access so that a lot of folks can try out and learn along the way. So coming up, I want to plug a couple of immediate ones. We have an Educator Summit coming. Do sign up. Hopefully, as part of that, if you want to offer courses, if you want to structure courses, if you have queries, if you want to know more, this is a good thing to sign up for and ask questions and queries. Hopefully, and also share knowledge across different other like-minded folks so that we offer better courses along the way. The other also equally exciting thing coming up is for gamified self-paced learning for high schoolers. I'm quite excited. It's going to be launched in August to help students at high school or little beyond to remove all the other complications, technical things, but through games learn the quantum skills. I think that is very exciting. I'm very happy, very curious to see how this comes about. I'm hoping that there will be wider adoption, and we'll have people right from high school, even if they don't know the concept or theory of it, by playing games, they would have learned intuitively how it works. And the hope is that the next generation will come a lot more prepared than my generation, perhaps, into this space. So with that, that's the end of my talk. I'm happy to take any questions.
Thank you very much for this informative lecture, and with the information what you have provided in the paper. And I should thank you very much for this. Now I invite any participant who can have, actually I saw a lot of hands raised, some queries. They can come forward and put their question and clarification. Thank you. Please come one by one.
I have a genuine curiosity, if I can ask a question. I wonder why IBM not go for error correction or just demonstrating some kind of logical operations with the number of qubits we have now. And I mean, why it's waiting to go till 1,000 or 10,000 qubits to demonstrate error correction?
So a couple of reasons. One is that the noise regime that we are at, we need to be in little better quality for us to actually leverage error correction. But that said, the generation prior to error correction would be error mitigation, and to do things that we could do to get the better result out of the hardware that we have. So you do need a lot more qubits to do effective error correction, a lot more qubits that are cleaner to use it effectively. Or else what's going to happen is that you're going to spread it out wider, because idea of error correction is to encode in a bigger space, which means you're taking one qubit and encoding it in a lot more qubits. And then you have more sources of error. And therefore, it's there. Once you spread it out, the error is going to become more and more dominant. So it's a balance. It's not that people are not looking at it. It's just that at the right time, probably once we have a lot more qubits at hand, which are a little bit better quality, then that will come about.
That makes sense. Thank you.
Thank you. Next question. If any questions there, kindly come forward fast, because we will go to the next person. Actually, he will be presenting a paper. Last chance for anybody to come forward and put a question in doubt. I hope there is no more questions or any to ask you, sir. I thank you very much. For my side, there is from Rohit Teja. There is a question: how does IBM work on having the same problem? What is that actually? Can you please read it out again, Mr. Teja? If he's in the panel, he raised a question here. Hello? Okay. Let us go ahead. And thing is, this error correction normally, and I know that, when we go very deterministic and probabilistic, that's what you told, right? How you marry these two? Because anyway, the industry looks for a very deterministic approach, and definitely your computing has definitely gone in the proper direction to arrive at it. So how you have married about the error correction, that is how the error will be deterministically controlled in our particular use of the quantum mechanics, quantum qubit?
So there is a, let me see. Okay. So there is a formal theory behind it in terms of error correction and in fault tolerance that shows that if you encode this particular qubit, a general state of a qubit in this particular form, that is, in other words, you perform this set of gates and you encode it into a bigger set of logical, and form a logical qubit, then and if you have the appropriate error threshold, then eventually what will happen is the correction starts dominating the noise, and therefore it keeps you in the subspace. So there is a full-fledged theory behind it to show that you can encode it in a higher space as long as with certain constraints like error threshold that is there. Then the correction of it dominates the noise that wants to take you out of the subspace and keeps you in that subspace of this. Think of this logical blob as logical state of that system. It keeps you inside that blob. It doesn't let you go out of it. But for that to happen, you need to have certain threshold that needs to be met in hardware. And that's why I said error correction is a little further out. Otherwise, it will go out of the logical space. And so there is no value in doing error correction at that point.
I will go a little bit forward.
Is there a question?
No.
Okay.
Please talk something relevant, actually, otherwise you can unmute. And I'm telling you, I want to take one step forward. What is the type of noise, what you say in this quantum qubit? What do they do? Because definitely that is a limiting factor. What is the type of noise? Because in noise in the classical system, we know that. But what is that actually you are telling about the noise, which should be controlled? Yes, if the noise is less, definitely the error is less. How do you define a noise in the quantum qubit?
So for example, there are many sources of noise in a quantum system, and my comment should be limited to the superconducting qubit technology that we are using.
Yes.
Because it has to be tied to a physical realization, or else you talk theoretically, which is slightly different. In the context of the particular realization, in this case, superconducting qubit, so what you have is this qubit, which is essentially an artificial atom. And that we use the lower two energy levels of this artificial atom for the qubit state, 0 and 1. And then the way we talk to it is through a microwave pulse that we send it across for it to do all the gate operations. All right. So what can go wrong? One is this is a quantum system. So naturally there could be decoherence, which means that our energy can drop. That is a source of noise. And that can happen, that typically is controlled by the external entities. If I'm in a very refrigerated space, even a photon floating around, a single photon can potentially disrupt the state, take you from 0 to 1 or 1 to a higher level energy, and therefore it disrupts the overall thing. So what happens is we keep it in a very cold refrigerator and we operate in 15 millikelvin, which is really, really, really cold. Plus we keep it very dark so that there is no even fringe photon coming in. Even with that, it's not that you completely can isolate these systems. So for example, I have a qubit and this is a microwave pulse connected to it through a waveguide. You're going to have other waveguides connected. Naturally, you're going to have some coupling potentially. In physical systems, you're going to have interactions that can happen. Many times you cannot control everything completely. Sometimes you want them for proper reasons. For example, the 2-qubit operation that we have to do is through a coupling between the two adjacent qubits. And so you shine a light in a higher frequency than the frequency of operation of this particular qubit in order for us to perform the 2-qubit operation because there is coupling between them. While that coupling helps in doing actual 2-qubit calculation, it's an open channel now, which means that it can induce noise in the system. And so that is another source of noise. Then you perform any operation when you shine a light or microwave pulse at it. I mean, everything has to be precise for it to work the precise way. We have, for a single gate operation, we are getting into a 99.9% regime. That is, we are having quite a bit of control. But even minor defects here or there can cause things to be different, and therefore it will cause problems.
Yeah.
Finally, the act of measurement. So that is another source of error. So all these are different sources of error that is purely due to the quantum physics of the system.
Thank you. Actually, to summarize this, you have told that it is the KTBN noise, that is from the noise temperature, and the coupling factor, and the defect in the manufacturing, and art of measurement. These are the 4 factors which.
These are the immediate 4. There could be others more sophisticated,
major
but I'm giving you
factors,
the major ones. Yeah.
Thank you very much from my side.
Yeah, thank you, Dr. Raghunathan. It's a pleasure to hear from you. And hopefully in the future also we'll interact more.
Thank you, sir. Thank you for the opportunity and all the very best.
Thank you. Now, actually, the next paper will be presented by, I think, Mr. Pramanik. Am I right? Mr. Pramanik.